Let's talk about another formula that, one more concept is called the center of pressure. So when you have, if you add up these verticals and these horizontals, I'll draw a new picture. Here's our dam. Here's our vertical. Here's our horizontal. These guys intercept right here. And my actual resultant FR is the vector sum of the F horizontal plus the F vertical. The F horizontal and the F vertical intersect right here. My FR passes through that point, and this point where this FR touches the surface is called the center of pressure. It's an interesting term. We don't really use it for anything. If you're taking a moment or actually doing a statics problem, you basically would consider FH at this acting at this point, and you would consider F vertical acting at this point. And so the point at which FR intersects that surface is really more of a theoretical construct. I mean, if you went down there and inspected the curved surface, you wouldn't find anything special about that point. So it's more theoretical, but it shows up on tests from time to time, center of pressure. And so you need to know the term, center of pressure. One more formula that's interesting is, and I'm going to show this one to you first before we talk about integration. So I basically said that if you have an odd-shaped, so a non-constant width plate that is submerged, like a circle, a triangle, a parabola, a half circle that is submerged, you end up with a pressure distribution on that that's very complex. So this is a circular cross-section at some depth. You got a pressure distribution. Again, the pressures increase linearly with depth, but we don't have a number. We don't have a formula for this. I didn't draw that right because basically the pressure at the top here is not zero. So we don't have a formula for that. But fortunately, there actually is a very convenient formula, which I call it the GZA formula, because gamma in Greek is G, gamma, and then Z, and then A. So you would call it Gaza, maybe. That's one way that I used to remember it, Gaza, or GZA. And so the resultant force is equal to gamma times Z bar times area. So what are those terms? So you basically have this submerged plate, and the C is the centroid of the plate, and Z bar is the distance from the free surface down to the centroid of the plate. That's Z bar. Gamma is the specific weight of the fluid, and area is the cross-sectional area of the plate. So it's actually a pretty simple formula. So if you're in the US system and your gamma is 62.4 pounds per cubic foot for fresh water, Z bar and area, that's how you can solve a problem that way. What's super valuable about this formula is that, and we'll look at how to integrate these shapes, but it's way easier than integrating to get these FRs on these shapes. And so these problems often show up on an exam. And certainly on an exam, you don't want to set up an integral if you could help it. Just use the gamma Z bar times area formula. And we're working, in fact, I'll show you an example. So here's a problem. This is an interesting problem. So this is a problem worked three ways. And so this is basically a dam with that comes up to a free surface, and it's 20 foot high. There's a 30-degree angle face on this dam, and it has some length L. So L times cosine 30 is 20. So this length is 20 divided by cosine 30, which is 23.09 feet along this face. And so we want to find the FR acting along this face. And of course, the dam is 10 foot deep. And this is fresh water, so we're going to use gamma is 62.4 pounds per cubic foot. So if we take the triangular distribution, FR is 1/2 of the base of the triangle times the height. So the pressure at this 20-foot depth is 20 gamma, so that's the base. The length of this face is 23.09 feet, and the distance into the board is 10 feet. So FR is 1/2 of base times height times the depth. And if you do that math, you get 144.1 kip, or thousands of pounds, perpendicular to the face, which is 30 degrees below horizontal. And it acts 1/3 of the way up from B. And so if this length here is 23.09 feet, 1/3 of that is 7.7 feet. And so that's a great way to work this problem. Questions on that? Pretty straightforward. Okay, well, we can work it another way. How about horizontal and vertical? Can we do that? So horizontal and vertical, we pretty much have to use that for curved surfaces. But you can also apply it to something like this. And so if you take the same problem and say, well, there's a horizontal that acts of a triangular distribution, and there's a vertical, which is the weight above this triangular plate. So the horizontal now, 20 gamma is still the pressure here, but now the length is 20 because it's this vertical guy. It's not the 23.09, it's 20. And so the horizontal is 1/2, 20 gamma times 20 high times 10 foot into the board. So the horizontal is 124.8 kip this way. The vertical is the weight above that guy. And so it's this cross-sectional area, which is, and this D here is 23.09 times sine of 30, which is 11.55 feet. And so my weight here is the area, which is 1/2, 20 times 11.55 times the depth into the board, which is 10, times my gamma, and I get 72.1 kip as my vertical, the weight above it. And then the FR, you can write as a vector, is 124.8 I minus 72.1 J. But if you find the norm or the magnitude of that guy, it's 144.1, just like we found from the triangular distribution. And so inquiring minds want to know, well, can we use that gamma Z area formula? Let's give it a try. So let's try that guy. So basically, here's the same problem, and it's actually a relatively easy approach. And so these are tools in your toolbox, different techniques that you can use. So FR is equal to gamma times Z bar times A. So Z bar is the depth to the center of the stem. And if this is 20 foot deep, the center is 10. So Z bar is 10. Area is the area of this plate. And so remember, this plate is 23.09 feet long, and then it's 10 feet into the board. So the area is 23.09 times 10. And then finally, gamma is 62.4. And so if you take gamma times Z bar times the area, you get 144.1 kip. You get the same number. And so we've basically worked the same problem 3 ways. And so realize that you can use these tools interchangeably on some of these problems, and it's pretty handy.